Okay, we are ready to start. Today we are glad to have Zak Mhammedi presenting. Zak is a research scientist at Google Research. He focuses on reinforcement learning and optimization. He completed his PhD in computer science at the Australian National University, and he was a postdoc in MIT. Zak aims at bridging the theoretical and practical gap in AI, in particular developing efficient reinforcement learning algorithms. He presented works at top conferences like CORT, NeurIPS, ICML, and he received several oral and spotlight awards. So we are really glad to have you here presenting today, and thanks a lot for accepting our invitation. The stage is yours. Thanks a lot.
Well, thanks a lot, Luca, and thanks for everyone for coming. So this talk is going to be a little bit on the theoretical side, technical side, I should say, but I try to keep the math to a minimum. But if I'm going too fast over certain things, please feel free to ask questions. And I guess before I start, I would say that this project is part of a broader effort of bridging the gap between practical RL and theoretical RL. So if you look at what's used in practice, typically people use things like PPO. These algorithms are simple and practical, but they often fail in exploration tasks, even simpler ones. And on the other hand, you have what people have in theory. So there can be an exponential separation in the statistical complexity between theoretical algorithms and the one used in practice. But typically, the algorithms used in theory, they are computationally inefficient, or they make very strong assumptions about the environment. So this highlights a big gap in our understanding of what of how can we make RL sample and computationally efficient. So in particular, I want to understand what conditions on the environment for MDP will allow for sample and computationally efficient RL. And in this paper, I consider a special setting called linearly-realizable MDP. So the setting, in the setting for all, we assume that for all policies pi, there exists some parameter theta pi such that the state action value function is linear in some known feature map phi. Okay, and so here the state action value function is just the expectation of the rewards to go. Okay, so this assumption is simple, but it is still much more general than linear MDPs. So linear MDP here, I'm sure you're all familiar with it. You assume that the transition operator is linear in some feature map phi, so you have this low rank structure. And okay, so focusing on this linearly realizable MDPs, I'm interested in can we have an algorithm that is sample and computationally efficient under online access to the MDP? And so more precisely, the question is, does there exist an algorithm A that can find a policy pi hat such that with high enough probability, this pi hat would be epsilon optimal, and the algorithm would only need to use a number of episodes and computational cost that is polynomial in all the relevant parameters of the problem. And in particular here, we don't want to depend on the size of the state space. So we only depend on the dimension of the feature map, but not the size of the state space. So the state space here can be infinite. So for this particular paper, we're going to aim for something a little bit less ambitious. Instead of aiming for something computationally efficient, we're going to aim for something that's oracle efficient, meaning that we want an algorithm that makes a polynomial number of calls to a standard oracle that's used in machine learning. So this particular oracle is a cost-sensitive classification oracle. But okay, so before I move on, let's first compare this assumption to other assumptions made in the linear function approximation setting. Well, as you know, there's the linear Q star, where you assume that the optimal state action value function is linear in some feature map phi. And this setting is actually known to be statistically intractable, unless you assume you have some value function gap and you have some local simulator. But in the standard online access without any additional assumptions, this setting is intractable. Then you have linear Q star V star, This one is statistically tractable, but not computationally tractable, again, in the online RL setting. And then you have also things like linear Bellman complete, where it is assumed that the Bellman backup of any linear function is also linear in the given feature map. So this setting is interesting because it has recently been shown that it is statistically tractable, but you have to pay exponentially in the number of actions. And so, okay, so all these settings and all the results that I just mentioned, they are relevant to RL with online access. So online access means you have an agent that can interact with the environment and generate trajectories. And this is the setting we're interested in this paper. There is a slightly stronger setting that's been studied called local access. So this is the same as online access, but you have the additional ability to reset the agents to any previously visited state action pairs and then start generating trajectories from there. So that's what we call local access. Many of you may be more familiar maybe with the generative model or random access model. So this is a model that allows you to reset to any state action pair, even the ones that you haven't visited. And this is, of course, much stronger than local access. So when you have local access, it does make many of the settings in linear functional approximation setting tractable, but that's not going to be the focus of this paper. We're going to focus on online access alone. Okay, so given this assumption, what we want is a sample and Oracle efficient online algorithm for this linear QPy setting. So what we know for this setting is the following. We know that it is tractable both statistically and computationally when you have this local access or local simulator. So again, this is an Oracle that can allow you to reset to any previously visited state actions. And we also know that in online access without resets, this is statistically tractable, but not computationally tractable. So this is a recent result by Gellert and Chaba. But yeah, we don't know of any computationally efficient algorithm for this setting. So the main result is, well, we will show a sample and Oracle efficient algorithm for this linear QPy setting. In particular, I'll show you an algorithm called optimistic PSDP that returns a policy pi hat, such that with high probability, this pi hat is going to be epsilon suboptimal. And it does this with polynomial number of episodes of interactions with the environment, and also a polynomial number of calls to this standard Oracle that I'm going to describe in the next slide. And so note that, you know, if you want an error suboptimality epsilon, the sample complexity depends on poly 1 over epsilon. And again, there's no dependence on the state space explicitly, right? State space can be infinite. And what's interesting here as well is that the number of calls to the Oracle does not scale with 1 over epsilon. So this is just poly D and H. Okay, so this is going to be the guarantee. This is the main result of the paper. So before I describe what this cost-sensitive classification Oracle is, do you have any questions about the motivation or, yeah. Yep, sure.
Hey, can you hear me?
Yep.
Yeah, so this is all for the QPy realizability setting, right? I mean, under the assumption that the value function can be realized. Okay.
Yeah.
So because we know for example, Q star, V star, it is computationally hard, then both of them are realizable.
Yes, exactly. So, right. So I clarify here that we don't show something computationally efficient for linear QPy. We show something that's Oracle efficient. So it makes polynomial number of calls to this Oracle that's somewhat standard. I'm going to actually show you in the next slide.
Right. Thank you.
Okay. So the cost-sensitive classification Oracle is defined as follows. So given a sequence of costs, states, and actions, the Oracle requires solving this minimization problem where it's a weighted sum of indicators. So pi here is a function from the state space to number of actions. So this can be interpreted as a classification problem. And in fact, it can be reduced to binary classification. And this pi bench is some policy class that I'm going to construct for this specific problem that we care about. And it has like it will have an explicit functional structure. And some things to note here is that this specific oracle that we use, we show that it can be implemented computationally efficiently in constant dimension. So meaning that if you're happy with exponential in D, then this can be implemented efficiently. But in general, because this is classification, it is NP hard. But it is often, we solve these types of problem in practice all the time. And as I said, you can still reduce it to binary classification.
I guess, like here, what you mean by this constant in D is for some specific choice of the set of benchmark policies, like softmax or something.
Well, for the specific benchmark, like I choose a specific benchmark class.
Okay.
And I show for that specific benchmark class, you can do it end-to-end computationally efficiently if you're happy to pay exponential in D.
Yeah, but I just meant to clarify that it is, because I'm like, there is D in it. I'm like, okay, the benchmark, like as written on this slide, doesn't have any D in it. So it's like, what is D? It's going to be clear later when you choose the benchmark.
Yeah, well, D here is the dimension of the feature map.
Right, like, but the benchmark class has nothing to do with the dimension of the features, does it?
Well, it has features, like we define the benchmark class.
Once you define it, it will be clear that it's related to the
Yes.
features, but not now. I just like a small remark.
I agree.
Okay. And then NP hardness is also for some specific choice, I guess. It's like related.
True.
Yeah, okay.
And yeah, okay, I guess one more thing to say here is that this is still still significant because we know that there are some RL algorithms that are not even compatible with Oracle efficiency. So for example, RL algorithms that are based on global optimism, like Golf or Olive, we know that some of them are incompatible with Oracle efficient implementation, right? So even if you're happy with this like exponentially in D to implement the Oracle, you cannot actually implement them, right? So this actually, there's a separation between this and some really like computationally inefficient algorithms for RL. Any questions about the Oracle before I move on?
Oh, yes. So the N samples, are they like IID or the Markov samples?
So the Oracle doesn't care. Like you just give it a sequence.
Oh.
I mean, in the actual algorithm, like maybe they will be IID or something, but like the Oracle just needs to take in a sequence and generates the argument.
Okay, thank you. Yeah.
Okay. All right. So, okay, I guess I'll immediately jump to maybe limitations and open questions before I dive into the details of the algorithm. So ideally, we want something that's end-to-end computationally efficient. And like ideally, we don't want to be dealing with an Oracle at all. So that is still an open question, whether we can come up with an algorithm that's end-to-end computationally efficient. I also have a poly number of action dependence in the sample complexity. So this was not, in the previous sample efficient algorithm, they don't have any poly A dependence. And this obviously limits to settings where the action space is finite. And of course, lower bounds. If this setting is not computationally tractable, we still don't know of any lower bounds. So that's also another open question. So for the rest of the talk, this is what we're going to go through. First, we're going to look at some properties of this linear QPy setting. Then I'm going to show you a very simple algorithm when you have this local access model. Then we're going to generalize the algorithm to online access. And then I'm going to go through maybe a proof sketch of the method. Like what are the key challenges and ideas that we use. So, okay, starting with this. I'm going to show you two key properties of linear QPy realizable MDPs. And for that, I need some definition. So the first is I'm going to define something called the range of a state. And with that, I'm going to define property 1. Then I have another couple of definitions before I show you this second property of this linear QPy realizable MDPs. Okay. So, and please feel free to ask me any questions in this part. So the range of a state is essentially just the worst case difference in Q function when you vary pi. So you vary pi and you look at Q pi xa minus Q pi xa prime, and you want to look at the largest difference, right? So what's interesting about this range of states is that states that have a low range, they don't matter. And actually, this is easy to see because states with low range, then by definition, it doesn't matter what action you choose, the Q function is not going to change. So intuitively, it doesn't matter what you play on those states. And actually, you can show something formally about this. You can show the following. So given two policies, pi and pi prime, if I now define a new policy in red, this pi tilde, to be basically equal to pi on high range states, but is equal to pi prime on low range states, then essentially the value of this pi tilde is not going to be much worse than the value of the policy in blue. Right? So this means that you don't lose much by just doing something random on low range states. Okay, so you can basically ignore them, like if you want. Is this clear? What I mean by the definition of a range of states? And yeah, okay. So before I move on, we can write the range of states in a slightly different way that's going to be more useful downstream. So because we have this linear Q pi assumption, we can write the range of states by taking the supremum over this theta space. So the theta space here is just the space of thetas as you vary pi. So theta pi is this parameter that's defined in the definition of a linear Q pi. Okay, so we have equality here, and this is going to be useful. Okay, so now we're ready to show this property number one. So property number one says the following: given any function f and any policy pi tilde, if you multiply f by the indicator that the range is high, so now you basically zeroing out f whenever the range is small, then the conditional expectation of this indicator times f is going to be a linear function. Okay, so in the linear MDP, this is always true. In the linear MDP, the conditional expectation of any function is going to be linear. But here, what this result says is that if you're not in a linear MDP, but you do have this linear Q pi assumption, then you can take any function and multiply it by this indicator for the range to be like non-zero, and that is still going to be a linear function. So this is kind of like an almost MDP result. So here's an idea. If somehow you're given this range of states, what you can do is apply LSVIUCB, which is an algorithm for linear MDP, apply it almost as is, but whenever you have a function, just multiply it by this indicator for the range to be greater than nu, and basically you will be done. Because in a couple of slides ago, I also showed you that it doesn't matter what policies do on low range states, so you can safely ignore them, right? The issue is that we don't have access to this range of states, right? And so the natural question here is, can we build some sort of proxy or surrogate for this range of states? And so I'm going to give you an intuition of how we might go about building this range of states. So consider this theta space that I showed you before. And now consider the symmetrization of this theta space. So if you look at the convex hull of this symmetrization, this is going to be a centrally symmetric set. So we know from convex analysis that there exists some ellipsoid that sort of like hugs this theta space. So this theta is going to be sandwiched between this ellipsoid up to a root d factor. And so if you have such an ellipsoid, then, well, first of all, the range of states, you can write it also as a supremum over the symmetric theta space, right? Just because we have phi minus phi of a prime. So this is equality. And so if you have this ellipsoid, you can basically approximate the range up to some up to some like root D factor. Is this clear? Yeah, so this only follows from this sandwiching that we have here. So basically what this says is that we want to find some symmetric W that defines an ellipsoid that sort of approximates your parameter space as well as possible. And that will give you a constant approximation of the range function. Okay, so before I show you how we do that, we need a couple more definitions. So I'm going to define something called a valid preconditioning. And I promise we're almost done with the definitions. A matrix W is called a valid preconditioning if there exists a sequence of vectors Wi's such that this matrix here has this specific form. So it's the inverse of the sum of the Wi transpose, where the Wi's are non-zero. And it also has this property that the inner product with any theta in the parameter space is going to be less than 1 in absolute value. And finally, you require that the Wi's are sufficiently different from one another. That's what this like third condition specifies. Okay, this is a complicated definition, but what you need to take out of it is that if W is a valid preconditioning, then we have at least a one-sided, so this theta space is going to be included in this ellipsoid up to a factor of D. Okay, so ideally we want both sides of inclusion, but we only have one, and that's going to be enough for what we need. Okay, one more definition, and then we'll be done with definitions. So I'm going to define this slightly modified feature map, which takes in also as input a matrix W. So this AX and A prime X are just the action pairs that maximize this norm difference. Okay. And with this, now I'm going to tell you what we're going to use as a proxy or as an approximation for the range function. So if W is a matrix that is a valid preconditioning, then our proxy for the range function, which I am defining as the norm of this modified feature map, is going to be, greater than the range of X up to some factor of square root D. So the reverse side of the inequality here doesn't hold. If it did hold, then we basically be done, because we only need a constant factor approximation for the range function, but we only have one side here. I know I skimmed through a lot of definitions so far. Like, any questions here so far? What am I defining as the range function? Please don't hesitate.
Hello. So even I don't know like the definition of the big theta h and the symmetric. Yeah.
The definition of the big theta h.
Yeah. And the big theta h system. Yeah. Oh.
So the top left.
Top left, and our system, let me see, minus or plus minus or symmetric.
No, even above that. So, so this guy
I
here, right?
see. Okay, and
So
then
it's
you
the set of parameters as you vary pi.
Okay, and then you want to find out ellipsoid that contains the symmetric set.
Yeah. What about it?
Oh, so after that, then the range can be like we can get an upper bound of the range. Yes.
I mean, if you have an ellipsoid that sandwiches your this one, then you get you get an approximation up to a constant up to a factor of D, right?
Oh yeah, got it. Okay, thank you very much. Yeah.
But I guess if you have this valid preconditioning, we only guarantee one-sided inequality. So we only have an upper bound on the range, right? But I'm going to show you that we can still do, because of our choice of this proxy, we can do a little bit more.
Okay, thank you.
Okay, so the idea is, well, we hope to, by switching this range function to the norm of this var phi, we hope that we're going to get something that will make the conditional expectations linear. But that's going to be not going to be exactly the case, just because this proxy for the range, we only have a one-sided inequality. But this is where the second property of linearly realizable QPy MDPs is going to be useful. So what this property says, if you're given a valid preconditioning matrix W, then one of the following is going to hold. Either you have the following, either the expectation of your function f times the indicator for this proxy of the range is small. And by the way, this is not a conditional expectation. This is just a marginal expectation. So either this is small, or because of our specific choice for this var phi, you can compute a new vector W such that W is non-zero, and you can and then you can update this matrix. You can compute a new matrix W tilde that is also a valid preconditioning. Okay, so this part here is crucial. So like, let's take a moment to see if it's completely clear. So this is what this is saying is, again, there's a property of this linear QPy MDPs that, because also of the choice of this proxy, either we have that the expectation of this f times indicator is approximately linear, or we can update our preconditioning matrix, right? And so whenever we update the preconditioning matrix, we're essentially having a better approximation of the theta space. Okay. So this actually gives us an idea of what we can do algorithmically. So algorithmically, what this means is, yes, John?
Yeah, so what's L here compared to H? I forgot.
Oh, L is just some like stage after H.
Next
So,
stage?
like a layer. So it's any layer like after H. Yeah.
Any later stage?
Yeah.
Okay. Usually you did this for one stage, but
yeah, we need it for more than one stage here.
I see.
But this property holds for any stage. It doesn't matter which stage it is.
Yeah, that makes sense, I think. Yeah. Because
So this second property is going to give us some idea of what we can do algorithmically. So what this says is, okay, if you somehow witness a bad linear fit, then you can update your preconditioning matrix and refine the approximation of the theta H space. And what's also very nice, because of the definition of the valid preconditioning, is that you can only update this preconditioning of order d times. So this will eventually stop, and once it stops, then you're guaranteed to have a good, like approximate linear fit. Okay, so this gives us a hint of what we can do algorithmically. And of course, so this f and pi tilde, like I left them unspecified here, but they're going to be prescribed by the RL algorithm, right? So we're going to see what f and pi tilde we're going to require. So essentially, f is going to be bonus function, and pi tilde is going to be pi hat that the algorithm computes. Okay, so summary of the properties. So property 1 says that linear QPy MDPs are almost like a linear MDP. If you know this range function, you can always multiply by the indicator of the range. And property 2 says that if I use this proxy for the range instead of the range itself, then one of two things happen. Either we have a good linear fit, or we can update, we can refine our approximation for this theta H space. Okay, so these are going to be the key properties that we're going to use in this paper. So it's worth maybe, like, if you have any questions, please ask, so that we are on the same page. Now I'll quiz you after if you don't ask. Okay, no questions. Okay, so we're done with the properties for the linear QPy. Now let's have a look at probably like a very simple algorithm for when you have this local access. So the algorithm for local access is inspired by this PSDP algorithm, policy search by dynamic programming. But it has additional components, and it actually is a special case of two recent algorithms. One of them is MTSS. So this is actually, in this paper, the first paper, we have an efficient algorithm for this setting for linear Q star beta MDPs. So you have a KL regularized MDP where Q star beta is linear. And there we show that you can have a computationally efficient algorithm. So I actually, that paper is interesting. So I'm doing advertisement here for it. And this algorithm is also a special case of this RVFS. And this is a paper that I talked about a couple months ago. So okay, let's jump into the algorithm. So the algorithm takes in as inputs parameters delta and epsilon and returns a policy pi hat. First couple of steps, you're just doing some initialization, nothing interesting going on here. The first interesting step is a dynamic programming step where you start from the last layer, capital H, and you go backwards. And what you do is you call a subroutine that sort of fits the value function. So this phi transpose theta hat is going to be an approximation of your Q pi hat. Okay, so you're doing this dynamic programming. You start at the last layer and you go backwards. And the second component, actually this component is not present in the standard PSTP algorithm. So this component here, its purpose is to identify state action pairs that are uncertain. So as you're finding your pi hat, you might be visiting new state action pairs, and this subroutine will just do rollouts and see if you've find some state action pairs that were different from the ones you've seen before. And it keeps growing a set of state action pairs. And the final step is you just evaluate your pi hat and you keep track of the best pi hat. And that's the one you're going to return at the end. Okay, so there's three components. There's the first component, which is the dynamic programming of fitting the linear, the value function. The second component is you look for state action pairs that were different, and then you just keep track of the best policy pi hat. I'm going to very quickly skim over what this subroutine does. So essentially, you iterate over state action pairs in your core set, and then starting from those state action pairs, you roll out, and then you see if the state action pair XHAH has a large elliptical bonus, and you basically return the one that has the highest elliptical objective. So that's going to be the most uncertain state action pair. I'm not going to go over the details for this algorithm. I just wanted to give you a very high-level idea of what this is doing. So that was the algorithm for local access. It's okay if you didn't get all the components of it. I just want to give you just like a high-level structure. Now we want to generalize that template to the case where you don't have local access. And by the way, you need local access for this algorithm because once you pick a state action pair, you need to be able to generate trajectories starting from that state action pair, right? So that's where you need the local access. You can't have this in online access. Okay, so starting from this, the algorithm for online access is going to look very similar. But it fits optimistic, it fits value functions plus bonuses. That's why I call it here optimistic PSTP. So this part of the algorithm is very similar, except now this is going to be an approximation of the value function plus the sum of the bonuses, right? And now instead of having a set of state action pairs that we keep track of, we now have a set of policies. So you can think about this as a core set of policies. So you can think about them as kind of like a policy cover. They try to sort of explore all directions of the feature map. And then the second component, again, this is you're gonna search for policies whose expected features point in new directions. And you're gonna look among composition of policies. So you vary pi in your core set of policies, and you then mix it with this pi hat. Okay, so one issue that we have, one technical challenge here is that this part here, the expectation of the bonus, is not necessarily going to be linear. And so this is problematic if we are fitting this objective with a linear function, we need the expectation of the bonuses to be linear, right? So this is the main challenge. And actually, what do we choose for the bonus? So the standard choice of the bonus, if we are in a linear MDP, is just to choose the elliptical bonus. This is a standard bonus in linear MDPs. But this is not going to work because we are not in a linear MDP, and so the expectation of the bonus is not necessarily linear. But we do have this property that I told you before, that if we take any function and multiply it by the indicator for the range to be non-zero, then this is going to be linear. And so the better choice is to multiply by the indicator using this proxy for the range. Okay? This is going to be our bonus. And still, because this proxy for the range only gives us a one-sided inequality for the actual range, the conditional expectation here is not going to be always linear. So we need something else. So instead of aiming for the conditional expectation, we're going to be satisfied by just having linearity marginally. So as long as we can, the expectation of the bonus times this indicator is linear in expectation, this is going to be enough. This is going to be sufficient to show optimism. Okay? And if it happens that this error is large, then again, because of this property number 2, we can update this preconditioning and refine our approximation for the theta h space. So this is property number 2 that I showed you earlier. And as I said also earlier, this can only happen ordered d times. So eventually, once you've updated this valid preconditioning d times, then you're going to have this approximate linear fit. So this fit opt value will return these like updated preconditioning vectors. So they are 0 if and only if we have this approximate linear fit in expectation. So here I recall that the bonus is just the indicator times the untruncated bonus. And this will hold true if you can fit approximately linear fits the individual bonuses. So for all else in the future layers, if this is small, then everything is good. Okay. So as long as you can fit this approximately, then these W's are 0. And this is sufficient for the analysis. And as long as they're not 0, then we can update our valid preconditioning and have a better approximation of the theta h space. So these are non-zero at most ordered d times. Any questions before I jump into the analysis? No questions? Chaba, everything clear?
Yeah, I see my questions later because they're not that relevant for here, but yeah.
Okay. Sounds good. All right, so I'm going to quickly go over some of the challenges and key ideas behind the solution beyond what I just said now. So when you analyze PSDP, you typically need to show these two inequalities by induction. So you start from L equal capital H, and you want to show these two inequalities here, where V is just your optimistic Q function evaluated at pi hat, and Q tilde here is the optimistic Q function, but minus the bonus at the current layer. Okay? So again, I'm just recalling the definition of the bonus is just the indicator times this untruncated bonus. Okay? So if we are able to show 2, suppose we do this induction successfully and we show both 1 and 2 for all L from H to 1. If we show it for L equal 1, then we are basically done after doing the following. After substituting pi tilde with pi star, that's kind of like the benchmark policy we want to choose. And after we relate Vt, which is on the right-hand side of equation 2, to V pi hat of t, because that's the quantity that we are actually interested in at the end. And we can relate the two using a standard elliptical argument. So is it clear why, like, if we have 2, we are done? Yep. Okay. At least Chaba agrees. So let's move on. Okay. So let's see how we can do this induction. So suppose we have 2 for L equal H plus 1, and we want to show 1. So just by writing out the definition of Q pi tilde is just the reward at the current time step plus the conditional expectation of the value at the next time step. So we can use equation number 2 to have this upper bound. So the upper bound V pi tilde by Vt. And just then use the definition of Q tilde. This is exactly Q tilde. So if you have 2, you can show 1 pretty easily. The heavy lifting would be to show number 2. Okay, so suppose we have 1 for L equal H and we want to show 2. There is a standard decomposition. I'm not going to go into the details, but you can show the following. So you can show that V of pi tilde is less than this V tilde of t. So V tilde of t is just Vt, exactly what we want, minus the bonus at the current time step. And these two terms here are regression errors. And we need to bound them by the bonus if we are to show number 2. Okay? So let's see how we can bound these two terms if we are in a linear MDP. So if you're in a linear MDP, then Q hat minus Q is linear. And so you can do a change of measure without going into the details. You can bound the regression error at XA by the elliptical objective at phi of XA times the algorithm's regression error. This is the regression error like on the rollouts of the algorithm, right? So typically this is going to be less than epsilon, and so you can show that this error is going to be less than the bonus. And then we are done. So if you're in a linear MDP, things are easy. Now back to the linear QPy setting, the problem is that this is not linear, and so it's more tricky to do this change of measure. And typically we want to set this pi tilde to be pi star. So what we're going to do here, we're going to make our life a little bit easier by relaxing this benchmark policy. So instead of choosing it to be pi star, we're going to choose it to be something else that will then allow us to bound these regression errors. So the choice of benchmark is going to be the following. This pi hat star, I'm going to set it equal to pi star on high range states. But on low range states, I'm going to set it to be equal to pi hat. So very earlier in the talk, I told you that if you define a policy in this way, because it doesn't matter what the policy does on low range states, your policy pi hat star is going to be almost as good as pi star. So this is good. So by doing this relaxation, we're not losing much if we're happy to compare against this pi hat star. But the nice thing about choosing this pi hat star is that now whenever the range is small, the whole error here is going to be equal to 0. Right? So I'm going to test you to see if you're paying attention. So why is this useful?
We want 0 errors.
Well, it's useful because of this property. So I told you earlier that any function f multiply it by the indicator for the range to be greater than gamma, then this is going to be a linear function. So if you choose this benchmark by hat star, you are essentially, it's as if you're multiplying by the indicator, right?
Sure.
So if you define ftx to be this error, then as long as you choose pi tilde to be equal to pi hat on low range states, then this conditional expectation is going to be linear. This is following just from property number 1. Okay?
Wait. Oh, okay. So you're calling this whole right-hand side the f function. Okay. Whose conditional expectation you take. Got
so
it.
you can see that when pi tilde is equal to pi hat, like these two terms will cancel, right?
Yeah.
Yeah.
Yeah. Got it.
So that's why this then allows us to say that the conditional expectation of this f thing is going to be linear. And this is good because then we can do the change of measure, right? So we can write then this expression in terms of the regression errors for the algorithm's regression errors. And we need this pi prime to be, either equal to pi tilde or pi hat. Okay. So a quick note here, which is we need this regression error to be small for all pi tildes in this benchmark class, because we need to include pi hat itself and like the choice of pi hat star. And it is precisely because we require this regression error to be small for all pi tildes that we require this classification oracle, because we need to do some optimization over policies in this class. So if we can remove this requirement here, then we'll get something that's end-to-end computationally efficient, but I don't know how to remove it. But anyway, let's come back here. I think hopefully I convinced you that by changing the benchmark policies, you can do this change of measure again by going one step backwards, because we're going to here to h-1. And so you can write this as follows, right? So there's still an issue here. What is the issue? So we managed to bound this f by some bonus at the previous layer. So is this it? Are we done?
Well, this bonus better not be larger than the bonus that we had at this stage.
It might not be what, sorry?
Well, we want the bonus at the current stage, not the bonus of the previous stage.
Sure. I mean, there's a way to massage this induction to make it work, but that's not the main issue.
Okay.
So the main issue is this is an untruncated bonus. So this does not have the indicator multiplying it. And in the definition of this optimistic value functions, we needed to have this bonus that's multiplied by the indicator.
Okay.
So this is a problem because the V's and the Q's are all defined with truncated bonuses.
Right. Got it.
So how do we solve this?
It's the range. You flip it.
Well, okay. So this was very, very much an annoyance to solve. But here's what we can do. There is property number 3 that I haven't showed you yet for this linear QPy setting, which is you have a slightly more general result where you include also the indicators at intermediate stages K. And why this is useful is because in the analysis and also algorithmically, it would allow you to essentially just skip over any state that has a low range. I'm not going to go into too much detail, but like we can use a much more elaborate value decomposition that includes the ranges from all intermediate states. And that effectively allows us to solve this issue for like the untruncated bonus. So when we do this more involved decomposition, we can get the truncated bonus instead of the untruncated bonus. This is too much detail, but like I just wanted to give you just a high-level idea of what's going on.
Just indicate the pain.
Huh? Just indicate
the pain that went into.
Sure. I only have 4 minutes left, so I just want to quickly show you what this benchmark policy class is. So let's define a base policy class, which is just the argmax of a linear function. This is not, we need something a little bit more elaborate than this. So we're going to define this benchmark policy class to be pi is in the benchmark class if and only if there exists some theta i's and some pi prime and pi double prime, such as pi is a combination of this pi prime and pi double prime. By the way, does D now become a little bit more clear why it comes from this? Yeah, okay. So it kind of looks a little bit funky, but I showed that as far as minimizing the function, minimizing over pi bench is not much harder than minimizing over pi base. So just aesthetically, this looks a little bit more complicated, but from optimization perspective, they're pretty much the same. And what we can show is for some range function that's like a constant factor away from the actual range, this is going to be in the benchmark class. And this is all what we need for the analysis. All right? Because remember that I told you that we needed this pi hat star to be in the class. Well, this is going to be almost like pi hat star. Constant approximation of the range are fine. And what I said earlier, we needed to be able to do this optimization problem. Again, we can do this in exponential in dimension and poly in anything else. But yeah, so that kind of brings me nicely to the end of the talk. Again, reiterating the questions. Ideally, we want an algorithm that is end-to-end computationally efficient and without requiring an oracle, and removing poly A dependence if possible. And I guess by now I'm kind of convinced that I don't think there's any computationally efficient algorithm for this setting, but lower bounds could be nice. And yeah, I'm happy to take any questions now.
Cool.
Great. Thanks for the talk.
Thanks, Luca.
Yeah, how do you do this clapping? Let's see. There you go.
Any questions?
Sure. Who wants to start?
Gergely maybe wants to say something. Are you muted, Gergely?
He has a hard time unmuting himself. Yeah.
Oh, geez. Okay. Sorry. No, thank you. No, I don't think I have too many questions. I've seen this in the rips, and it's really nice.
Yeah.
Yep. Sure.
Hi. I guess I'm wondering, if there's some cleaner structural property than the QPy that you think leads to these sorts of algorithms, more directly in terms of this sort of range function. And it seems like you're sort of partitioning the space structurally in some way into useful states and unimportant states.
That's correct. Yeah. And what is the question?
Is there some cleaner, maybe more general structural characterization?
I can rephrase the question because I had a similar question. So my question was, it seems that the range itself, as a definition, is very independent. It's just independent of whether you want to model these functions linearly or not. Of course, the other parts of the algorithms are going to depend on this quite strongly. But the range function themselves, it just, do we have the range or not have the range? That's like an MVP property. And so I was wondering whether these properties would generalize to some other setting, that So intuitively, okay, so you said a few things. One is that low-range states do not matter in strong senses, right? Like you do random things at low-range states, it will only impact your performance so much. So that's very intuitive. So that seems to suggest that the range itself is like a useful MDP property. And there could be other settings, not just this linear QPy realizability setting, where the range function could play some role. So I was wondering whether you had any thoughts about this. Dhruv, is this aligned with your question?
Yeah, I guess it kind of felt a little magical, the fact that when you take the indicator of the range, you suddenly get linear. So I was wondering kind of if there's something deeper there. I think it's based similar to what you're asking.
Well, I think the fact that the range of states don't matter, that's more that holds more generally for any, I think, for any MDP. The fact that things become linear once you multiply by the indicator, that strongly relies on this linear QPy assumption. I was trying to use something similar for the linear Bellman completes, but I think for the linear QPy, it heavily requires it to hold for any pi, not necessarily, for linear Bellman complete, you need a specific, you need this linear policies, right? Like the ones that take the argmax of phi transpose theta. So yeah, not clear if we can use it necessarily beyond this setting.
Yeah, so my more general question that I was saying to the rest is that when you start with this spin of bridging the gap between theory and practice, great. I totally agree, it would be awesome. And it seems that the range is maybe doing something that could be brought to, brought in and could be folded into algorithm designs that maybe practically would also make a difference. Like intuitively, it feels that knowing that you have low ranges, although there is this ellipsoidal construction that is very specific to the linear case that allows you to essentially do all the work for knowing for which states you have low range or not. Like that's like a learnability question that kind of just comes out of the framework. So maybe one way of thinking more generally about this and bringing these questions or these approaches to more practical algorithms using neural networks, whatnot, would be to think about frameworks where the range can be approximated quickly somehow. And then how do you use that? And maybe that's actually something that could be practically useful and impactful as well, right? Because on one hand, there is this intuition that, yes, low range would be good to know. And you kind of simplify the MDP if you're filtering out, skipping over the low range states. And then you have a new MDP, and maybe that MDP has just some better structure. So it's bad distractions by the low range states are rejected, and somehow good things come out of it. Would this happen in practice?
I agree with those questions. I feel like, if I'm true to that first slide, I think I would say, I think what would be impactful in practice is considering maybe settings that are even simpler, where you have deterministic dynamics and...
Wait for a second. Okay, just the dynamics deterministic, rewards or not?
Just the dynamics, I think.
Yeah. So rewards stochastic. Yeah, that's complicated enough.
Yeah. I think the online setting here is kind of assuming stochastic dynamics and you don't have local access. But I think in actual real scenarios, things are deterministic. You do have local access, at least in simulation. So I think to bridge the gap to practice, I feel like focusing there is still going to be like, probably could be fruitful.
I see.
And I think the property of states that I think Shaba would agree that this is something that is not super understood in practice is like, how do you assess the uncertainty of a state action pair, right? In linear MDP or like this linear settings, you can just look at the elliptical bonus, but I think in general functional approximation, it's not super understood what you can do. I mean, there's this like R&D and there's all these other things, but I feel like that's kind of like a major question that has been underexplored, both like theory and practice.
Well, this is not too related to this talk, so I kind of feel bad about pushing in this direction. But since we are here, how about like algorithms that do not even use bonuses, right? So somehow you can implement optimism with this reward biasing idea, this reward idea by P.R. Kumar that's coming back, that you have, like the fitting criterion that you want to, like respect the data, and then you also want good reward. Okay, it's computationally horrible, but maybe you can massage it and like relax it and then make computationally efficient algorithms out of that. Whereas the advantage is that you don't explicitly deal with constructing bonuses. So it's like you're pushing the design problem somewhere else. I don't know.
I'm not super familiar with this paper. So what's the gist? So
very simply, it's like, so what is that you want? Like, let's say you're in a bandit, you have some data, you collected some data because you were interacting with the environment. Well, when you are modeling the reward, you want the reward model to reflect what's in the data, but maybe the data is not, incomplete, and you know that, like, okay, many possible reward functions are viable given the data. So amongst those, you want to choose the one that gives you the highest reward. You can just write an optimization problem for this, where you're training up the two things. One is that, like, what is the maximum reward that you can extract, and the other thing is like how well you're fitting the data.
Isn't this sounds like some global optimism thing to me?
Well, yeah, yes. It's a global optimism in a bandit that wouldn't matter that much. But then it becomes a question of massaging this criterion into some algorithm that's efficient, and it's not about explicit uncertainty quantification. I love an explicit uncertainty quantification too, but like it seems that we have a hard time making the next big steps there, and so that's why I'm wondering about these alternatives like this, right? So it's like a different design, but it has the same potential.
Yeah, I mean, I think I'm on board with like forgetting about bonuses and just I think the paper you have on sample efficient RL with local planning, I mean, there you tested different algorithms that were, some of them used bonuses, some of them didn't, but then they took advantage of like restarting at state action pairs that were uncertain. But I guess that comes back to like our ability to assess like what is an uncertain state action pair in general function approximation. So I guess there's two angles where you can approach this, either from like an optimization perspective or from uncertainty estimation.
Yeah, I mean, so maybe one general way of saying, like repeating what I was saying, or like emphasizing a little bit more, is that uncertainty quantification was not the problem. We made it a problem because we see that it would be useful, but maybe that's not the only way. There is no result, as far as I know, that is doing a reduction from online learning to uncertainty quantification, right? And maybe there will not be, right? That would say that if you solve all these problems in this class with a low regret, that means that you effectively can extract uncertainty quantification from that. Like, is that really true? I don't know. It feels maybe not true.
So what is the standard reference that you have in mind for these kind of estimation procedures?
So yeah, they're making some comeback. So let me push.
Because
some
this
reference.
idea appears in some of the DEC like work and also in
Yeah,
field sampling and related.
Okay, so let me give you a modern account from 2020.
Uh-huh.
There, just copy it in chat. So there were some follow-up papers today, but I didn't want to hijack the conversation completely.
Because I think that like something like this was used in some like DEC for linear MDPs like work. I think like Noah, Dylan, and Sasha.
Yeah.
There's because I guess like
you're getting off keyboard and how well you're fitting the model. Yeah, like
when you're fitting the model, it's not only the likelihood but also some bias towards models that promise you higher reward.
Yeah.
And then just bake this into the DEC objective is one thing that they did.
Yeah.
And I don't know how related it is to.
I mean, well, you know, all of these, the real question is like, but is it going to be computationally efficient and when, right? Like, even if, okay, so you say, I like this design criterion. I want to design my algorithms based on this reward bias idea. Great. Can we do it in linear MDPs? How do we do it? Okay, like to start with, and then can you do it in QPy realizability setting? How do you do it? Like, did you really avoid estimating the bonuses? Like, I don't really know the answers to any of these questions. I'm just throwing this in as an idea of that, like, since we have this trouble of going beyond the linear setting because uncertainty quantification seems to be like very unclear or very conservative. Like, we shouldn't say that like we don't have anything. Like, people have written papers about this, but somehow, okay, it's not computationally efficient ever. No, okay, so Lin actually wrote one paper where he is trying to reduce it to some other oracles. So there is some, if you have some very general optimization oracle that you can solve always, then somehow even uncertainty quantification and this optimism can be reduced to that. So that was at least one paper I know of that is doing that. So yeah, but people are not running these algorithms for sure. It's like, it feels like super duper expensive to, like, if you read that paper, it's doing a lot of subsampling, a lot of refitting, a lot of everything, and like by the time you would implement it, like,
I think you have an uncertainty measure in your paper that I like, which is like, you know, the bootstrapped.
Yeah,
that seems to work somewhat well.
Yeah, like, yeah, bringing randomization to the picture and using it to your advantage. But that I'm learning about that is that, again, the linear setting is somewhat friendly to these ideas. And for the non-linear settings, like, even if we go just a little bit beyond the linear setting, like generalized linear setting or like generalized linear cases, it becomes a bit complicated.
You mean in theory? I guess in practice it does.
That's right. But like, the theory actually tells you negative results as well. That like, if you do the naive thing, I can give you examples where you just went a little bit beyond the, like, some narrow class of generalization of the linear setting, and it already fails.
Maybe we should consider deterministic dynamics.
What we should consider?
Deterministic settings.
Yeah. That's another idea, actually. That at least the dynamics is deterministic. Because the only reason we not do that is to kind of have some robustness, field robustness, but maybe there are other ways of achieving that. Like the world, by and large, at macroscopic scale is deterministic, for heaven's sake. Newton. Yeah. Some phenomena are really hard to model like that. Like incomplete information pushes you into this corner where you want to use probabilistic models, right? Like, that's it. So now what do you do about that? This doesn't really mean that the world became non-deterministic. And so your algorithms necessarily would need to reflect that. No, maybe that other part of the algorithm that is modeling information needs to do things differently because of misspecification, incomplete information, and whatnot. But that's not the same problem as starting with a stochastic world. Yeah, potentially. Yeah. I don't know.
Right. I gotta run soon, but yeah, if anyone has questions about the paper or want to think about lower bounds or something.
The lower bound, definitely a good question, but yeah.
I have not tried lower bounds, like not much at all. So yeah, there could be some low hanging fruit there. I mean, maybe I should have spent more time on lower bound than banging my head against the wall with the upper bound.
Yeah. I mean,
so maybe Dhruv, you can you're good with lower bounds. So
yeah. Well, if the upper bound doesn't work for a long time, definitely go for the lower bound.
all right.
All right. Okay. Yeah. Good to see you.
Thanks.
Take care.
Bye.
Bye.
Right. Thank you, Zach.
Good to see you guys. Bye.
Bye.